My name is Ashton Morelock, and I'm a graduate student at Florida State University. And today I'm going to be talking about spectrum unfolding of 12-carbon DN using the Katrina detectors. Katrina is the compound array for transfer reactions in nuclear astrophysics, and it is composed of 32 deuterated benzene liquid scintillators. 16 of the detectors contain the scintillated material in a 4-inch by 2-inch aluminum cell, and the other 16 detectors contain the scintillating material in a 2-inch by 2-inch aluminum cell. Neutron energies can be extracted using their pulse height or light output spectrum through a method known as spectrum unfolding. An experiment analyzing 12-carbon DN was performed at the Edwards Accelerator Laboratory at Ohio University. Results from the spectrum unfolding of the 12-carbon DN reaction are presented in this work. Uncertainties generated through spectrum unfolding are also discussed. Here we have the light output spectrum, or phi of I, as a convolution of the detector's response matrix R and the neutron energy spectra psi. We can then employ Bayesian statistics and an iterative method to solve for our neutron energy spectra. So here we have the kth plus 1 estimate of the neutron energy spectra is dependent upon the previous energy spectra estimate, the response matrix, and the light output spectra. To get our light output spectra, we have to analyze the PSD, or the pulse shape discrimination of our detectors. This allows us to differentiate between neutron events and gamma ray events. Once we have identified the neutron events, here gated in red, we project them onto the x-axis to get our light output or pulse height spectrum. We have to then know our response matrices. So here we have the response matrix for our large or 4-inch by 2-inch detectors. And here we have the response matrix for our small or 2-inch by 2-inch detectors. If we go back up top, on the top two plots, we have the unfolded results for the 12-carbon DN reaction for the large detectors. And on the bottom, we have the results for the small detectors. In this left-hand plot, we have the light output spectra for our large detectors. And the original pulse height spectra or light output spectra is shown in red. And then we have a refolded pulse height spectra shown in blue. The refolded pulse height spectra is made by taking the last estimate of our neutron energy spectra and plugging it back into our original equation. In both of these light output spectra, we are able to identify the 13 nitrogen second and third excited state, the first excited state, and the ground state of 13 nitrogen. Then if we go over to our right, we have the neutron energy spectra. The figure made in blue is the unfolded energy spectra, and we compared this to a neutron energy spectra made using time of flight information, and that is in red. And we did this to make sure that we were seeing the appropriate peaks in the appropriate areas and with the appropriate counts. And you can see that for both detectors, they agree very well with one another. We can then look at the uncertainties generated through spectrum unfolding, and we do this with covariance matrices. So here we have the covariance matrix, which depends on the light output spectra, which is defined down here. And then we have the covariance matrix, which depends on the propagation of the response matrix and previous energy estimates, and that is defined right here. We can then apply these covariance matrices to our results that we saw earlier. So this is the results for the 12-carbon DN reaction for the small detector. And when looking at these errors, we found that the total error in our highest peak was only about 5% of the total peak counts. But then we looked at the ground state of 13 nitrogen, and we saw that the errors increased quite a bit. And this was due to the low statistics in the response matrix for the smaller detector at higher neutron energies, which is due to a lower efficiency at higher neutron energies. Then over here, we have the total covariance matrix for these particular estimates of the errors. So in the future, we still need to extract some spectroscopic information from the 12-carbon DN reaction using a time of flight and unfolding methods. And then we need to improve the response matrix for the 2-inch by 2-inch detectors, possibly through simulation. Thank you.